Today we're going to talk about vector fields. So a vector field is defined to be a function, and they can be in the plane or in the space or even in higher dimensions, but they take an input point, ordered pair in this case, since we're in the plane, and it assigns a vector to each point in that domain. Again, since we're in the plane, this will be a subset of R2. So the vector field F takes in points in the form of x, y, and puts out a vector. Here, notice that these two are scalar functions. And in general, as we've seen before, if it's got a bold, or when we handwrite it, we put a vector across the top, it's a vector output. And if it's just a regular handwritten variable, then it's a scalar output. So the component functions P and Q are scalar output functions. Whoops. Yep, so note the component functions P and Q are scalar, outputting a constant for each input. So here's an example of a vector field. Here our field is the vector field 1i, or in other words, the x component 1, y component 0 at every single point. So if we were to ask, hey, what is the vector associated with the 2, 3? Well, then our output vector would be 1, 0, because it doesn't actually depend on location. And if I head over here to my graph, I go to 2, 3, that looks like it's right about here. And with vector fields, you start your output vector at the input point. And since we're going 1 in the x direction, it would look like that. If you're looking at this, you can maybe imagine that if we continued doing that at every single point, you can kind of see that grid. Oops, let me do that right. I went half length, but that's 1 in the x direction. So from 2 to 3 there. And similarly, if we went to the point 2, 2, it would be 1, 0, and we'd have a vector there. So if you're looking at this and thinking, well, why are you drawing those long black vectors, but all the vectors that are shown are blue? It's common to kind of scale down the size of a vector when you're plotting a vector field. And there are a bunch of resources linked on the site for you to explore, so that you can kind of get a bigger feel of what's going on. Because this is a fairly simple example, but what if these vectors depended on their location, the output vector? So say we had xi plus yj, then all of a sudden, let's name this vector field, I don't know, for lack of a better name, let's call it G. And then we say, okay, well, what is G of 2, 3? Well, that would be the vector 2, 3. All right, so we'd head over to 2, 3, and I don't know, I'll switch to blue. Well, that's a poor choice of colors, and switch to red here. All right, so 2, 3, right about here. And it looks like we go over 2 in the x direction, so 1, 2, about there, and then up 3, 1, 2, 3. It would be like this. And if you plotted all those vectors on top of each other, I mean, so far we're focusing just on what I'm going to call coordinate grid points, so 1, 1, 2, 2, not things like 1/2, 1. Well, we could do those as well. Any input point will have a related vector. It's going to get cluttered up really fast if we leave them like that. So it's common to scale these vectors down. And we'll see another example of this as we go. So plowing forward. Here's another example where the component functions are -y in the x direction and x in the y direction. That's just for fun. We'll calculate one. So f of 2, 1, I don't know, that works. All right, so -y would be -1, and positive x in the y component would be 2. All right, so heading over to our initial point, 2, 1, looks like it would start something right here. And then we would go -1, 2. All right, so it would be like that. But as you can hopefully clearly see, let's just say that this little blue vector there, they've scaled it down and it looks shorter than the ones around it. Well, all of these over here that are even longer still means they're going to have an even bigger magnitude than the red one we just drew. And all of these ones in here close to the origin that have really, really small ones, those have been scaled down as well. So they're a little bit longer as well. Here's kind of a fun one. X component function for this field is sine of x plus y, and the y component function is cosine of x minus y. Just kind of examples to look at and think about. Right, a vector field is called continuous if its component functions are continuous. And just like most of the ideas we've seen so far in multivariable calculus, these concepts that we're working on introducing in the plane extend on out to 3 dimensions and beyond. So if you're working in space, a vector field in space takes input ordered triples, and gives you a vector output. P, Q, and R are common. Otherwise, some texts use M, N, and P. So some texts, I think the Apex calculus uses M, N, and P. But I stuck with P, Q, and R here, which I think is what the OpenStax text does. All right, so here's an example of a vector field in 3 space. The vector field's X component is 1. Oh, there's the typo. First one of the day. 1/2, there we go. The Y component is 1/2 Y, and then the X or the Z component is 0. Now, 3-dimensional vector fields aren't so much fun to look at just in a flat way, but I put a couple of really nice plotters that you can look at, and you can change your view and get a better feel for what's going on there. Okay, so if we're asked to sketch a vector field, I won't ask you to sketch anything in 3 dimensions, but sketching them in 2 dimensions is a pretty good exercise. So as with many things, making a table is a very nice way to organize things, but for each input, ordered pair x, y, you're going to calculate and write down and then sketch the related output vector with the initial point starting, the initial point of the output vector starting at the input point. Oftentimes after you sketch a few and kind of get the idea of what's going on, you kind of find, okay, I can scale down my vectors like this, and it's going to make it more clear what's actually happening. So for an example, let's go ahead and do one. In this case, our field is 1/2 x in the x component function, 1/2 y in the y component function. And I went ahead and just calculated a whole bunch of points here. So, all right, at 0, 0, we've got this little guy right there, the origin vector. All right, and now at the point 1, 0, so we're over there at 1, 0, and it looks like we're going to go 1/2 in the x direction and 0 in the y direction. So there we go. There's our vector there. I'll just use colors. Why not? Oh no, I know what I'll do. Yeah, here we go. All right, so I took that back. Not going to use colors yet. So 0, 1 has 0 in the x direction and 1/2 in the y direction. Negative 1, 0 has negative 1/2 in the x direction and 0 in the y direction. Input point 0, negative 1 in the negative y-axis, if you will, has negative 1/2 in the y direction, 0 in the x direction. A little typo there as well. Okay, now what about 1, 1? Well, over here at 1, 1, we have 1/2 in the x direction, 1/2 in the y direction. So it looks like we're going to have that. But that vector is actually a little bit longer than these other vectors. So let's use this color for fun. All right. Now on to negative 1 as our input point. Down here, we're going to have a very similar negative 1/2 in the x direction, negative 1/2 in the y direction. And similarly, if we went ahead and calculated these ones, you'd see that you get similar kind of pointing out away from our origin here. So now at 2, 2, well, here we have 1 in each direction. Those are even longer still. And if you went ahead and did all of these, you would see a similar thing happening. So what about we don't have here? Let's do 0, 2. F of 0, 2 gives us 1/2 times 0 in the x component and 1/2 times 2 in the y component. This is going to give us 0, 1. Okay, so these are getting even longer still. So I'm going to kind of show these in this color. If you did that on all 4 of the places where 2 is involved on the axis directions, you'd get something like that. So it looks like as we're kind of going away from the origin, the vectors are getting longer and they're pointing away from the origin, if you will. And if we use technology to graph this thing, this is what our plot would look like. But notice again, well, 2 things. Let's talk about 2 things. Let's talk about choice of color. oftentimes red is used to show longer things, and hot, longer, and blue, cold, kind of shorter things. And so if you look at this, they've scaled those vectors right around the origin here, very, very short. Whereas you get out here by over here 4,4, well, 4,3 would be really significantly long off of our screen. And so they've scaled those to be red to show they're longer, but they are longer even than the scaled down blue ones in the center. But you can really nicely see this kind of radial outward pointing field pattern we have. So a unit vector field is just a vector field in which the output vectors all have a magnitude of 1. And you can take any field you have and do that by dividing the component by the magnitude of f. And this process is called normalizing the field. So then you're just looking at a bunch of unit length vectors. So our next topic is gradient fields. Recall that we've seen the gradient before. The gradient of a differentiable function, scalar function f, is the field of gradient vectors. All right, so another typo made me hiccup a little bit. So yeah, that's definitely not supposed to be added together. These are a vector. We know the gradient outputs a vector. So those are not addition signs, but rather commas. And so the gradient of a scalar valued function is just the partial derivative with respect to x in the I component. And that's, oh, no. All right, sorry, I just lost my thought here. That absolutely is a vector because we've multiplied it by the standard unit vectors. So yeah, we've seen the gradient before, but I kind of like it in component notation. The partial with respect to x, the partial with respect to y, and the partial with respect to z in the x, y, and z components respectively. So the gradient field of a differentiable function, if we have a scalar function, the gradient vector we've seen before and are used to working with is actually gives us a field, and we call this the gradient field. And so at each input, x, y, z, and this idea does extend down into the plane as well. We just chop off that z component. The gradient field outputs a vector. And what do we know about that vector? Well, we know that it points in the direction of the greatest increase of our function. And its magnitude is equal to the largest value of the directional derivative at that point. Again, yeah, notice that all these concepts extend to R2 as well. I just haven't typed them out. Okay, so let's do an example. Let's say, hey, we're given a scalar function. Let's find the gradient field, capital F, associated with that scalar function. And so the first thing we'll need to do is we will calculate the gradient. And so if we take the partial with respect to x of our function f right here, and drop down that 2 exponent on the x, and then leave everything else the same. Similarly, we can take the partial with respect to y, drop down the 3 exponent on the y, and then subtract 1 to get y to the second power, and leave everything else the same. And last but not least, taking the partial with respect to z, whoops, sorry about that, we get that expression. And that's it, we're done. We've found the gradient field. It's just calculating the gradient vector. So next concept is something called a potential function. A potential function of a vector field is kind of going the other direction. Say you're given a vector field and you need to find the scalar function such that the gradient of that scalar function gives you the field. But yeah, so if you're given a field, that scalar function f, that gradient is equal to that field, is called a potential function. And so that is capital F is equal to the partial derivatives of that scalar function in each of their component locations. And we call these types of fields conservative. So we're going to revisit how to find potential functions later, and we'll revisit it conservative vector fields in much more detail later as well. But for now, what we can do is we can verify that a function is a potential function for a field by calculating the gradient and checking that it matches the given field. So if we're given the function f is equal to x squared y squared plus x, We want to verify it is a potential function for the given field, 3x squared y squared plus 1 in the x component, and 2x to the third power y in the y component. So all we have to do is calculate the gradient of this function, the scalar function f. So look at scalar function f, and sure enough, if you take that partial with respect to x, you've got not bad at all. All right, I'll admit I got thrown again. I stole an example out of the textbook, and it looks like it's got a fairly big typo in it. So let's just continue with this example and see whether or not what we can learn about it. It says verify that f is equal to a potential function for this given field. Well, if it's a potential function, we want to answer the question, is this equal to the gradient vector for the given function of f? And so looking up here, we'd say, okay, f of x, the partial with respect to x is 2x y squared plus 1. Okay, well, that needs to be 2x y squared plus 1 for this to be true. And then similarly, the partial with respect to y is, so we drop down that 2xy, and then the derivative of x, the plus x term with respect to y is 0 because it's a constant, treating it as a constant. And so this one would have to be 2xy. So all is not lost. All we learned here is, let's change the word verify, and we're going to change it to determine. Determine if f is a potential function for this field. And so we checked it, and we didn't reach the same conclusion as what it originally was in the book, but rather we made some useful information. We said, nope, does not meet the criteria to be a potential function for the given field because its gradient vector does not match the field. Okay, now note it says a potential function here, and we use that language a lot when we're talking about potential functions, because as we'll see, there are infinitely many potential functions. You could just tack a plus c onto them. However, they are unique up to that constant term. So what does that say? Well, say we had, instead of keep the highlighting in yellow, keep the same scalar function, but say we were actually given this as the vector field. Well, let's name it G so we don't have two things of the same name on the same page. So V, or G rather, is 2xy squared plus 1, and then 2xy. Now f is a potential function for G, and that's a good one, but we could also come up with another potential function for the vector field G by just saying f1 of xy is equal to the same expression, x squared y squared plus x plus 1. And tacking on that plus 1 doesn't change any of the logic we just saw. We still get f1, the partial with respect to x is there, and f1, the partial with respect to y, is right there as well. So there are infinitely many. I could tack on whatever constant I like, because when you take the derivative of a constant, you get 0, so it doesn't actually impact anything. Sound like integration? Well, we'll see that that's part of the process of finding in potential functions when we tackle that later in a later section. Okay, so a little bit more on conservative fields here. So let f be a conservative field given by p, q, and r for its component functions, and let those component functions be differentiable on the domain of f. Then the mixed partials will be equal. That is, if we have, okay, so it says f is a conservative vector field. That means there exists some function f, little f, a scalar function, such that the gradient of f is equal to our field f. Okay, so then what do we have here? Well, then for potential function f, we would have equal mixed partials, because the individual components of the vector field are already first partials of our potential function. And so equal mixed partials, second order partials on the right there. If you don't look at the left, you say, okay, well then if I take each of those component functions and check their mixed partials, they should be equal. As long as this thing's a conservative vector field, we have that conclusion. Oftentimes, however, we leave out all of this highlighted kind of logic. We don't talk about the potential function. We just know it's there. And we just check the partials of the given component field functions. And they are written over here like that. And that's typically how it's written. But I wanted to take a minute to try and relate this back to the definition. And if you read the definition or this in the textbook, you'll notice they use the term mixed second order partials. And I think it can be a little confusing because second order partials would look like this. Let's take this one, for instance. Well, that's, whoops, partial, not proper. There we go. The second order partial, which matches that, our mixed partial there. And so that's why they use this. Let's see, I can do a little better even still. And this expression, remember that this, kind of taking off one of these partial symbols on the top, partial of f with respect to x, well, that is this, which is why we take and we use the remaining partial there. Hopefully that made a little bit of sense. I just think the notation and the language of which they talk about it can be a little bit confusing. The key is what's highlighted in green. The mixed partials of the component functions will be equal as long as you have a conservative vector field. So conservative vector field implies mixed partials are equal. Similarly, you can apply this idea to a vector field in two space as well, but there's a lot fewer partials to check. Okay, so again, emphasize the last two slides, conservative vector field, if you have one, then you know that the mixed partials have to be equal. Be careful though, this is a one-way, not a bidirectional relationship. Just because you have equal mixed partials does not guarantee you that you have a conservative vector field. And again, we'll revisit the conservative vector fields later. We'll get into that. So we can verify a vector field is not conservative so far by showing that its component functions do not have equal mixed partials. We are not yet sure how to determine if we have a conservative vector field. Coming soon. So let's verify that f is not a conservative vector field. And in our example, f is going to be the field y in the x component, x in the y component, and xyz in the z component. So we have to check our mixed partials. So the first one we'll check is the partial of the x component with respect to y. Is it equal to the partial of the y component with respect to x? The partial of p with respect to y, is it equal to the partial of q with respect to x? Oops, I went 2 slides, sorry about that. So what do we have here? Well, let's grab that p function is y, and we're looking at the partial of that with respect to y. That q function is x, and we're looking at that with the partial with respect to x. So in this second line down, the partial of y with respect to y equals 1, and the partial of x with respect to x equals 1. And sure enough, this works. Everything's good. Give ourselves a green check mark, and we're good. So those first partials were equal. We gave ourselves that check mark there. So now we're going to move on to the next pair of potential partials, if you will. So is the partial of the x function with respect to z equal to the partial of the z function with respect to x? Partial of r with respect to x is equal to the partial of p with respect to z. Well, once again, we'll do the same highlighting thing here. P is equal to that, and that's where we have that. Q is, I'm sorry, not Q, but R is equal to that, and so that's why we have that. And so we take on the left, the partial of y with respect to z is 0, and the partial of xyz with respect to x, well, derivative of x is 1, so just the yz comes along, which is definitely what that should say, not 1, that should say x z. I should say yz, what I said originally, not what I wrote or said the second time. And sure enough, no, they're not equal. And so this, at this point, we're good enough. We know it's not a conservative vector field. And so, yeah, since our that pair of mixed partials are not equal, then we know that f must not be a conservative vector field. Now this is unnecessary. Once we know that, it doesn't matter whether the third pair of partials are equal or not, but just in interest of being thorough here, we're going to finish this example out just for practice of calculations. All right, so Q is X. So we're looking at the partial of Q with respect to Z. And then R is XYZ. So we're looking at the partial of XYZ with respect to Y. And on the left, you have the partial of X with respect to Z is treated as a constant. Derivative of X with respect to Z is 0. And then on the right, you have the derivative of XYZ with respect to Y as XZ. And so again, they're not equal. It tells us we have our field is not conservative. And that is it for today.